We now begin section 7.7 talking about complex numbers. This section serves as a bridge from chapter 7 into chapter 8. So there's some concepts that we're going to cover that we're going to need to use quite a bit in chapter 8, but it's also linked to chapter 7 in that we're still dealing with radicals. In fact, we're revisiting a question that we had back in the earlier sections of this chapter whenever we decided to eliminate from all consideration having radicals that, or even radicals that contain negative values. For example, the square root of negative 4. If you were to come across that in a problem, you would have immediately said that's not a number, or not a real number. All right, well, we can, in fact, answer that question by introducing a new type of number, a number that we haven't worked with before, but a type of number that will allow us to answer the type of question where you have radicals underneath, or sorry, negatives underneath radicals. All right, and it's not so unusual to introduce new types of numbers to answer new types of questions. Historically speaking, in mathematics, we've done that all the time. Whenever we introduced negative numbers, that was introducing a new type of number to solve subtraction problems. What if I subtracted a larger number from a smaller number? I needed a new type of number. We're going to talk about negative numbers. When we introduced division of integers, we had to talk about fractions. That was a new type of number. When you introduce radicals, square roots of, say, square roots of 2, right? You can't use fractions to answer that. You've got to have decimal numbers to answer that. Decimal numbers with infinite expansions that don't ever repeat themselves. So historically, we always introduce new types of numbers that we haven't dealt with before in order to answer new types of questions. Now we're getting into worlds that leave the real world of numbers and talk about complex numbers. So we're answering that question of how do we take square roots of negative values. Let's talk about complex numbers. Let's begin by recalling that the square root of negative 1 is not a real number. That is, we cannot find a real number such that b squared is equal to negative 1. Because there's nothing that when squared is negative. So let us define the imaginary number so that we can take the root of negative numbers. We're going to define I to be the square root of negative 1. Now, I'll give you my opinion on the matter. I think this number is one of the most poorly named mathematical objects because it makes it sound as though we're pretending to introduce a new number. We're just going to pretend that this is a number. But in all reality, I equals the square root of negative 1 is a very important number, mathematically speaking. In fact, if you've ever driven in a car across a bridge, if you've ever flown in an airplane that did not crash, if you've ever used any sort of electronic device at all, you have depended on technology that utilizes mathematical analysis that includes complex numbers, the imaginary numbers. So it is very important to physics, to engineering, to mathematics in general to have this type of number. What's significant also about this number is that by introducing just one new number, we can now take the square root of any negative number. So look at this. For example, the square root of negative 4, I could write that as the square root of 4 times the square root of negative 1, right? Just using the product rule of radicals, which we assume is valid for these types of numbers, and it is. So square root of 4 is 2, square root of negative 1 is I, so that's 2I. Alright, square root of negative 9 would be the square root of 9 times the square root of negative 1, which is 3I. And the square root of 16 times the square root of negative 1 is the square root of negative 16, so that's 4I. And the point of this being that, we saw the same pattern all the way through. We can actually skip this middle step of splitting it up into two radicals. If we see a negative sign underneath the radical, we can immediately pull it out as an I. So if I have the square root of negative n, that would be the square root of n times I. Although in many cases I'll tend to write the I out in front of a radical just so that there's no confusion of where the radical itself ends. You know what I mean? Okay. So we know what the imaginary number is. What is a complex number? Let's begin by defining a complex number by talking about two numbers, a and b. We'll let those be real numbers, and any number of the form a plus bi, that is a real number plus a real number times I, where I is the imaginary number, is called a complex number. So if A is that first number, A is going to be called the real part. And you have plus bi, the number that's times the I, not including the I, but the real number that's times the I, will be called the imaginary part. So consider a few example complex numbers. If I start with the complex number 3 plus 7i, it's a real number plus a real number times I. The real part would be the 3. The imaginary part is the 7. Not the 7i, but just 7. Okay? Similarly, if I have 5 minus I square roots of 3, then the real part is the 5. The imaginary part is everything that's times the I, where that includes the square root of 3 and the negative. So that would be the imaginary part of this complex number. The number 6. That actually is a complex number because I can write that as 6 plus 0 times I. 0 times anything is 0, so that's clearly the same thing as 6. So it is still a complex number. That is, every real number has a real part equal to that value, and the imaginary part is 0. Okay? Likewise, you can have a purely imaginary number, something like 8i. Right? The real part is 0 because we can treat this as 0 plus 8i, making the imaginary part 8. And just to make sure it's clear, another purely imaginary number would be like negative I squared of 7. The real part is 0, and then the imaginary part is everything that's times the I, so a negative square root of 7. Okay. Now this line is significant right here. This tells us that every real number, the type of numbers that we've already been talking about all semester or all throughout this course, is all those real numbers are also complex numbers. So by introducing this one new number, the imaginary unit, we have now created a larger set that contains our previous set. Right? All real numbers are also complex numbers, but not all complex numbers are real numbers. We have a lot of those types of statements in mathematics. At this point, I'd like to remind you that we have this same sort of pattern where you create larger and larger sets with the new types of questions that are answered as you go through mathematics, as you start at the very lowest level and start with what are called natural numbers, sometimes referred to as counting numbers. Right? The numbers you learn whenever you're a child, you start counting 1, 2, 3, 4, 5, 6, and so forth. Those are the natural numbers. This symbol that I have in between each one of these means a subset, or is contained in. Okay, so these natural numbers, the counting numbers, are like 1, 2, 3, and so forth. At some point, you begin to realize that there's such thing as a 0. You know, if I ask you how many apples do you have and you look down in your hands and you don't have any, that you can refer to that quantity, an actual number of apples, 0 as an absence of that quantity. So that concept is what's introduced when we talk about whole numbers. Those are the numbers 0, 1, 2, 3, and so forth. Notice how all the counting numbers are also whole numbers. You just added the 0. But then when you start talking about what are called integers, you introduce basically subtraction to whole numbers. You're going to be able to subtract any two whole numbers. You want to be able to have negative numbers as well. So integers are like negative 3, negative 2, negative 1, 0, 1, 2, 3, and so forth, right? So all the way down negative, all the way up positive. Those are integers. So all whole numbers are actually in the set of integers. There they are right there. When you get to the next set, Q, is what we call rational numbers. Those are P over Q. Those are fractions, where P and Q are integers. Okay? Now, because every integer can be written as itself over 1, every integer is rational. So again, you've made it one step bigger. And then when you get to real numbers, all of the numbers that we've talked about preceding this is contained in the set of real numbers. They're all decimal numbers with infinite expansions. It just means that your decimal after the decimal point, your digits are all zeros, right? So like 1 is the same thing as 1.0000000, so forth. So all these numbers actually are real numbers. Okay, now we claim that all real numbers are in fact complex, and if I didn't emphasize this earlier, this is the symbol I'm using for complex numbers. Now, any real number can be written as a complex number, right? You can do a plus 0I is the complex version of the real number a. So, as a diagram, here's what we've got. We've got a big box, right? Those are all complex numbers. Call those the complex numbers. Okay. Now inside there, we have two groups, right? We have what would be the purely non-real numbers, like 2 plus 3i, or 6 minus 4i, or 2 plus I square roots of 3, or just I square roots of 5, 6i. Those types of numbers are non-real numbers. But we also have over here real numbers, right? Now that group of numbers can be split into two. All right, let me do it. Let me illustrate that this way. We'll draw a line here. So here's my real numbers. We can split those real numbers into two groups. Okay? You can have what are called irrational, like square root of 2, square root of 3, pi, negative square root of 7. Those are irrational numbers. And then you have the rational numbers. Okay? Rational numbers being those numbers that can be written as a fraction. Oops, let's try that again. Rational. Okay, so inside the group of rational numbers, you have a group of numbers that you might refer to as integers. Okay, now there's also numbers like 1/2, negative 2/3, 27/4, numbers that aren't rational, that aren't integers. But inside the integer set, you have things like negative 3, negative 2, negative 1, but inside there you have then the whole numbers. Okay, includes the number 0, but inside there you also have, finally, the counting numbers. One, two, three. So notice how each set gets bigger the further on you go until you get to the biggest set, which is everything complex. Fortunately, the hardest thing about complex numbers is understanding the concept of what they are. The easy part is doing the mathematics with them. Being able to add, subtract, multiply, and divide actually is the easy part of complex numbers, because all you got to do is this. You got to write each number in its a plus bi form. If it's not given in that form, you simplify it there, and I'll show you what I mean by that with an example or two. And then you add or subtract the real parts, and you add or subtract the imaginary parts. In fact, all it looks like is collecting like terms. If you think of I as a variable, even though it's not, it's actually a constant. But if you treat it like a variable, then it's really just collecting like terms like you do with polynomials. Okay? Actually, I should have put this right down here. Collect like terms. All right, then you write the answer back in that final form, the standard form. So if I had like a plus bi plus c plus di, you add the real parts, the a plus c, and you add the imaginary parts. So you get to b plus d, all that times I. And if you're going to subtract 2, you're going to subtract the imaginary parts, or sorry, the real parts, and you're going to subtract the imaginary parts. Just like that. It's even easier when you see it in practice. So look at this. You have 5 minus 2i plus 3 plus 3i. Notice we're adding these things together. So all I'm going to do is just get rid of the parentheses and have 5 minus 2i plus 3 plus 3i. Okay? Collect like terms. 5, 3. 5 plus 3 is 8. Minus 2i plus 3i is going to be plus 1i. 3 minus 2 is 1, so 1i. That's it. That's all there is to it. Subtraction's just like it, except you got to remember when subtracting, always distribute that minus sign. So you have 2 plus 6i minus 12 minus a minus 4i is plus 4i. Now collect like terms. 2 minus 12 is negative 10. 6i plus 4i is plus 10i. And you're done. That's all there is to it. Easy enough? Actually it is. That's all there is to it. Like I said, the hardest part about complex numbers is understanding the concept. The easy part is doing the mathematics that we're going to be doing with it in this course. Okay, we can add and subtract them. What about multiplying? Okay, multiplying is actually just about as easy as adding and subtracting. What you start with is a plus bi form again. Then you multiply. Now look, just kind of scan down here. What does that look like? Looks like a binomial times a binomial. And what do you use to multiply a binomial times a binomial? Right? You use FOIL. It's just like binomials. That is, just like it was a polynomial in X. Now it's just in terms of I. And then you use, and here's the extra step. This is the one thing you've got to remember. If you have an I squared show up in there, remember that I squared is just negative 1, right? Since by definition, we saw this earlier, I is the square root of negative 1. What that means then is if I square both sides, I is that number that if you square it, you get negative 1. I squared is negative 1 by definition. So simplify, you combine like terms at the very end. Okay, so look at this. We got 7i times 2 minus I. Those are two complex numbers. I'm just going to distribute. I'll do this in red. We're going to distribute. That's all FOIL is. That's all multiplying binomials is. And you end up with 14i minus 63i squared. Okay, now what's I squared? Negative 1, right? So I squared becomes a minus 1. So negative 63 times minus 1. To multiply in here is going to become plus 63. 14i plus 63, or if we want to write it in the proper order, a plus b, you got 63 plus 14i. Notice all the I squared does is change the sign. It's a negative 1, so it's just going to change the sign. Okay, let's do this one. 5 times 6, 30. Minus 7i times 5 is minus 35i. 4i times 6 is plus 24i. And 4i times a minus 7i is minus 28i squared. Okay, let's start with the last term. What happens? I squared becomes negative 1, so that becomes plus 28. Right, I have 30 and a plus 28. What about the middle terms? These are like terms, right? So I can go ahead and combine them. Negative 35i plus 24i is negative 11i. So I have 30 plus 28, that's 58 minus 11i. Did I do that correctly? Something seems fishy. Yep, that's correct. And there's my final answer. Here's a fun little question. What we've got is a polynomial function. F of x is equal to x squared minus 2x plus 2. And instead of plugging in a real number, I want to plug in a complex number. So I've got a function that I'm going to plug in this complex number into. Right? So as you know, f of anything is going to be you take that thing inside the parentheses and replace all the x's with it. You're just plugging it in. So f of 1 plus I would be 1 plus I squared minus 2 times 1 plus I plus 2. Okay, now let's simplify that. That 1 plus I squared is going to be 1 plus I times 1 plus I minus, and I can go ahead and distribute this, so minus 2i plus 2. Let's multiply out this complex multiplication. 1 times 1 is 1, plus the outside is 1i, the inside is 1i, the outside is plus I squared, minus 2 minus 2i plus 2. So that becomes, I'm going to write it out one more time. 1 plus I squared is minus 1. So minus 1, minus 2I plus 2. All I did was this guy. I squared is negative 1. Now combine all the like terms. I have 1, minus 2, plus 2. Notice how those all cancel out. And I have an I plus I, which is 2I, minus 2I, so they all cancel out. What happens if they all cancel? We end up with 0. So in this case, if I plug in 1 plus I into this polynomial, I get the value 0. This is a root to this polynomial. That's what it means to be a root, is it's the number that makes the function 0. That's not always going to be the case, but that's what happened in this particular example. We've multiplied, we've added, we've subtracted. What's left to do is dividing. I want you to notice that a division problem that involves complex numbers, if I were to take, for example, I don't know, let's do 6 plus 2I divided by 4 minus 3I. Notice how you've got 4 minus 3I in the denominator. If I is the square root of negative 1, this is basically a problem where you have radicals in the denominator. Right? So this goes back to what we did in section 7.5 when we were dividing radicals. There was a strategy that we employed to divide radicals. We had to get rid of the radical in the denominator. It was called rationalizing the denominator. Now, if we had one radical, it was multiplying the top and bottom by the same radical. In the case that we had two terms, like a 4 and a minus 3i, we used conjugates. Okay, recall that the conjugate of any binomial, including complex numbers, is the same two terms with the middle sign changed. So the conjugate of a plus bi is a minus bi. The conjugate of 3 plus 4i is 3 minus 4i. The conjugate of 1 minus I square roots of 3 is 1 plus I square roots of 3. And the conjugate of 2i, or in other words, 0 plus 2i, is 0 minus 2i, or minus 2i. So to divide complex numbers, we're going to multiply the numerator and denominator by the conjugate of the denominator. The effect of that will be to get rid of the I in the denominator, because it gets rid of the radical. I is the radical. In example A, we have 6 plus 2i divided by 4 minus 3i. We're going to multiply by the conjugate of the denominator, which will be 4 plus 3i. But we do the same thing on top and bottom so as to not change the value of the fraction. So now, because it's a binomial times a binomial both in the numerator and the denominator, we will use FOIL as our technique. So 6 times 4 is 24. 6 times 3i is plus 18i. 2i times 4 is plus 8i. And 2i times 3i is plus 6i squared. Okay, as we know, this is going to become a negative 6. We'll use that in our simplifying on the next step. On the bottom, I'll have 4 times 4, which is 16. 4 times 3i is plus 12i. Minus 3i times 4 is minus 12i. 3i, negative 3i, times 3i is minus 9i squared, which is going to become a plus 9. Now let's see what we have then. In the numerator, I have 24 minus 6, which is 18. I have 18 plus 8i, which is 26i, divided by the 12i's on the bottom are canceling out. 16 plus 9 is 25. Okay, now you can write your answer in this form, or just to emphasize the fact that this is still a complex number, split the top into two separate fractions. Write this as 18 over 25 plus 26 over 25 times I. Notice it's a real number plus a real number times I. The reason why I like splitting this up into two fractions like this is that it allows you to see what the real part and the imaginary part of the answer is. Right? When you divide two complex numbers, you should get a complex number as an answer, and that's what your complex number looks like. 18/25 plus 26/25 I. In example B, we're going to take the same approach. We're going to multiply the top and bottom by the conjugate of the denominator. In this case, it's actually a little bit easier because we don't have two terms. We just have one, but remember the conjugate for I is negative 4I. So multiply that on top and bottom. I still need to distribute on top, so I'll have a minus 12I plus 8I squared divided by negative 16I squared. On top, this I squared, 8I squared becomes a negative 8. So to write it in standard form, I'll have negative 8 minus a 12I divided by, now this negative 16I squared becomes positive 16, so divided by 16. Split that up, you'll have negative 8/16 minus 12/16 times I, but fortunately we can reduce both of those fractions. This becomes a minus 1/2. Taking an 8 out of top and bottom, I can take a 4 out of the top and bottom on the second one, so minus 3/4 times I. That is your answer on that division problem. Now we've done all four operations. I got one more thing I want us to look at relevant to complex numbers. The last thing I want to show you are the powers of I. It turns out, just like we had I squared simplifying down to negative 1, any power that is any whole number power of I can be reduced down to something in terms of just a number or just I. Alright, let me show you what I mean. I to the 0 power, in fact anything to the 0 power, is always 1. I to the first power is just I, right? The exponent of the 1 is understood. As we just saw before, this I squared is negative 1. And if you take I cubed, just split that up into I squared times I, and using the previous line, using the fact that I squared is negative 1, I squared times I would be negative I. So we got 1 I, negative 1, negative I. Now I to the fourth is going to do something interesting, in that we're going to have negative 1 times negative 1. It's going to give me 1. Okay? In fact, notice that corresponds right here. We begin a pattern that's going to repeat itself. I to the fifth would be I to the fourth times I, which is I. I to the sixth is I to the fourth times I squared, which is negative 1. I cubed times I to the fourth, or I to the seventh, would be negative I, and then I to the fourth times I to the fourth, or I to the eighth, is 1 times 1, which is 1. Okay? And then it does it again. I, negative 1, negative I, 1. And so I to the 13th would be I to the 14th would be negative 1, I to the 15th would be negative I, and I to the 16th would be 1. Okay? Notice how this is the same as I to the first, this is the same as I to the second, this is the same as I to the third, this is the same as I to the fourth. Now, how does 13 and 1, 14 and 2, 15 and 3, 16 and 4 compare? Well, it's this operation right here. If I were to take, say, 15 and divide it by 4, okay, using long division back from your grade school days, you'd say, okay, well that's 3. 3 times 4 is 12 with a remainder of 3. There is where that 3 comes from. It's the remainder that you get after you divide by 4. So to find I to any power, all you have to remember are these 4 values right here. You need to remember that I to the first is I to the second is negative 1, I to the third is negative I, and I to the fourth is 1. If you can remember those, actually, I wouldn't even remember this. I'd remember I to the 0 is 1. If I can remember these values right there, then I'm always going to be able to find I to the n by dividing by 4 and finding the remainder, and then I to whatever power is the remainder. It's that simple. Let's do it in some examples so you can see what I'm talking about in practice. I to the 35th. Right? Take 35, divide it by 4. 4 goes in there 8 times. 8 times 4 is 32 with a remainder of 3. So I to the 35th is I to the 3rd, which we know is negative I. So I to the 35th is negative I. That's it. What about I to the 81st? Take 81 divided by 4. Right, that's going to be, let's see, 2 times 4 is 8. 0, bring down the 1. 0 times 4 is 0, subtract. You get a remainder of 1. Okay, that means I to the 81st, the same thing as I to the 1st, or just I. So you can take any power of I and reduce it down to something that's either a number or just I. Okay? Alright, so that's the end of section 7.7. That's the end of chapter 7. Like I said, this section is a bridge to the next chapter. In chapter 8, we're going to begin talking about quadratic functions and quadratic equations and solving those types of problems. I know we've already solved quadratic equations before, but we're going to need some of the tools that we came up with in this section to be able to solve all of those functions. So that's where we're going next. So that's the end of chapter 7.